So yeah, today we're going to have a programming lecture, but I also want to remind us that this is week 15 right now. And so there are 17 weeks of classes. So this week, next week, the week after that, then we're done with classes. And week 18 is finals week. So there's only final exams that week. Okay? So, bam, reminder, you have a test coming up soon. I have made a little week 18 module for us that I will release a page out of right now for you. It's the final info page, okay? So you should be able to see that on our canvas right now. And yeah, so the final exam is just a scheduled time. There's a table somewhere. And this is what I read off the table. Hopefully I was right. But this is when I'll be here in this room for the final, at least. So it'll be from 4 p.m. to 5:50 p.m. on the Monday of finals week. So I guess it's nice to just get it over with. But we are scheduled to have our final on the Monday of finals week, starting at class time. But every final takes like an hour and 50 minutes. So a little bit longer than a normal class time, if you need that extra time. But yeah, here's what the final is going to be all about. It will have an essay just like the midterm with a certain number of word limit. Hopefully you can type fast enough to get 250 again, right? And then also, I could not test you on Scratch last time, but I can definitely this time test you on Python, because Python is just text at the end of the day. So get ready, prepare to write some Python code and put it inside of Canvas. Okay, so mentally prepare for that. I'm going to take my questions, the ones I'll make. I'll take them from the programming assignments and all the examples that I've done in class. But that's fair, right? So study those and you'll do well. Okay. For example, like expect to see the turtle module a bit, the random module, the math module, all those things that we've been learning and doing cool stuff with. Okay. And just like for the midterm, at least the majority, right? 51% or more of your points will go towards that essay about some sort of critical thinking topic. Okay? And just like for the midterm, the final exam is open book, open notes. You just got to be in this room. The only person you can talk to is me while you take it. No, okay? That's the idea there. Are there any questions about that? Do the logistics make sense? The topics make sense? All right, so yeah, if we're doing all right with that, you can read that page now. It should be available to you, but let's have a programming lecture now. So 2D bouncing is the idea today, and let's copy it in real quick. Dun, dun, dun. There it is. And so we're getting ready for this, right? We're trying to make it work. We know what we want to do now. We have that idea from the office, right? So we wanted to make that bouncing square that looked just like this, where we started out, right? We turned the turtle into a square. That was our game plan, right? And then we give him a random direction. Like any direction could be chosen, but we learned how to represent that and like send him off in that direction. And the second he hits a wall, bounce off in the appropriate way. And we learned how to do that. And hopefully, eventually, it'll hit the corner, just like in the episode. Okay? So remember, that is our goal. Let's go back to what we were talking about and actually code it up today. Okay, so here are some slides that are reminiscent of what we talked about last time. So our game plan is going to be, we're going to draw the boundaries of the screen. Okay, the boundaries of that screen. It's supposed to be a square, though. 400 by 400 rectangle with, this would be negative 200, right? Because 0 is right here. So we negative 200, positive 200. And this will be positive 200 on the x, negative 200 on the y. So those are like the bounds of our screen. And then we're going to make the turtle be a square in a random location within those boundaries, like set the x and the y of the turtle's center to be a random thing between negative 200 and positive 200 for both of those. And then we got to give a random direction, right? We learned kind of what it means to represent that kind of direction. It's a little bit over and a little bit up. It's always a right triangle kind of idea. And yeah, then it's a forever loop, just like for the bounce straight up and down idea. Yeah, forever, I would like the turtle to move in his current direction as long as there's nothing stopping him. Bounce, bounce, bounce. And if something finally stops him, like he hits a wall, then bounce off, not like don't do a 180, but do this, right? That's got to be the corresponding way to bounce off. And then once you eventually hit this wall, notice it with an if statement, and then bounce off that direction. You see how it's, I guess this was like a 45 angle bounce, and so it is really going to be 90 degrees, but if you're coming in this way, you'll bounce off kind of like that, so it's not always 90 degrees. It's the way you feel that it should be, though, and we've represented that. Yeah. So yeah, forever move in the current direction. We just have a second axis, move a little over and a little up, or a little left and a little down, stuff like that, right? And just like keep having a bunch of if statements, just like we did for the up and down motion. We just also need like 2 more if statements for the left wall and for the right wall. Okay. And so our lower level, let's see here, our lower level game plan looks like this. So we discovered that, okay, we'll make the turtle a square. That's perfect. And then he'll have coordinates that we can talk about where he is with, just like we were using for the ball. And the coordinates will always be relative to the center of that turtle. Okay, so like XY is where the turtle is right now. We'll have some variables to store that. And then we're going to store the direction that we'd like him to randomly move in, that random initial direction, with some offsets. Like if this is the turtle's direction, instead of having just a y offset like we did for up and down motion, now we'll have an x offset as well. It's like go a little bit over and a little bit up. That's how you create the effect of moving there. Yeah, so like you have an x offset and a y offset. And now, if you move that much in your x and that much in your y, you really will end up in that diagonal place. Isn't that cool? So that's the idea. And so yeah, the new location of the turtle now, if you started at x comma y, well, it's x plus x offset. That's the new direction for the x. X plus x offset and y plus y offset. See that? So that's going to be the idea there. Is that coming back to us? Any questions about that? Okay. So yeah, with offsets like that, we can make any two-dimensional direction. We can go this way, straight up if we wanted to, a little bit over. Like any direction we'd like, we can do it with those offsets. So that is our goal, bless you. And so, yeah, what we want to do every frame is move the turtle's x coordinate and y coordinate by that direction's amount. Just go a little bit in your direction. And then we'll have to talk about hitting that wall. Okay? So that's going to be the idea there. So then I also want to talk about normalization, but we'll get there. The idea is that every possible direction you could possibly want to move in will have an XY offset. Okay? So that is where we're going. So let's break open idle and try it. Let's, I guess at least for the draw rectangle part, we have a function for that. We also have the bouncing program. We can steal a lot from that, honestly. Let's do as much as we can from the normal, just original, straight up and down, constant speed bouncing program. So I'll go to that bounce.py that we were doing before. All right, so this is that code. I'm going to copy it into a new file for today. All right, and let's see. I guess the best name for it would be 2D bounce. And today's lecture number is, I don't think it's 26, maybe it's 27? Yeah, that's 27. Where is the file? This one. Okay, there it is. 27. And I'll call it 2dbounce.py. And I'll just paste in what we had before. This is the original bounce program, so I can close that now. And so this is everything we had before. Let's remember it. What did we do? So this is where we drew the rectangle. We still need that. That bounding rectangle, bounding square. We made the circle the ball, or the turtle. Yeah, the turtle became the ball turtle. We turned him into a circle, and we stretched him out a little bit. And then we set initial x and y locations, and this offset was at the y offset. Remember that. That was your up and down motion. Negative means you're going to go downwards, because we add that into our current y coordinate every frame. And so here are like the bouncing off the wall bits. So we'll keep all those. And then like after we determine where the turtle should be, actually put him there. After we clean things up and like make sure he's not hitting walls anymore. And we just do that all day long. Repeatedly draw a new frame, draw a new frame. Okay? Any questions about that before I change this to have two-dimensional direction? All right, this will be super fun. So, what do we want? Well, first of all, we would like a square. So let's turn that turtle into a square. How do we do it? You can go to the library page, but honestly, it's where we were up here. It's like turtle.shape, whatever you want. And one of those options, in addition to turtle and circle, there's a square option. Okay, we can keep him pink, or we can change his color, like make him purple. And you can just give a string here. So strings, remember, in Python can be single quotes or double quotes. Python doesn't care. And we can keep them stretched by that same amount, and the width of the turtle will still be 40. So that's kind of useful. So we're going to make the turtle the square this time. So if I rerun this, let me make this a bit smaller, actually. Now I have a purple square moving up and down. It's closer to what I want. All right, but up and down is not good enough for us. We've determined we'd like to move left or right, and then also we'd like to start at random places. You see this? We'd like to start at a random place that's not just like at the tippy top, because this is start at the tippy top for the turtle Y. See that? It's always, if I run the program, we're starting at the tippy top, but we would like to start at some random spot. Now, how can we fix that? Okay. So we're going to use these variables to keep track of not where the ball should be, but where the square should be and where it should move to. If I can spell square. There we go. And so, yeah, the x and the y can be both random this time. How about that? Random.randint. That could be all over the page. So let's say from, we do have to keep them within a certain range. Can't go too far out. Can't go straight to 200 because it'll be on the outside of a wall. But how about negative 150 to positive 150? That's fine because he's width 40. He won't exceed the bounds if I change it to those. And so now when the program starts, if I rerun it, oops. If I resave it and rerun it, now watch that the ball will still have an offset downwards. We're still moving down to start, but he'll start in a random location, random X and Y location. So there he was. He started over there, close to the bottom on the left side there. And if I rerun it, we'll get another random location. Now it's close to the bottom on the right side. Okay, so that's kind of nice. And the next piece of the puzzle is going to be the bouncing. The bouncing and the movement. All right, so let's see. What's our game plan? Forever. Move in our current direction, but our current direction is always down to start. So let's change that. We've learned, right? We've learned that we can represent directions with an X offset and a Y offset. So let's generate random numbers for an offset. Let's do that. Like this could be, I don't know, this is like 1, 1 or something, but it could have been just as easily 1, 0.5, and you'd move a little bit, not as far up as fast. So let's pick some random numbers for our X offset and for our Y offset. So this was just turtle offset. Let's make it two-dimensional now. All right. So let's do turtle X offset and then also turtle Y offset, and we'll set them to something in just a second. Because that's what we need to represent two-dimensional direction. Yeah. So these two variables together will form our direction. Okay. So all we want for them, right, is to be like within a certain range. It's just like go a little bit over, go a little bit up. Let's make them between like, let's make the X offset between +1 and -1, so like go that way or that way. And then the Y offset, let's make it between +1 and -1, so either go up or down with that amount. Okay? And randomly, it'll choose like something in between, something over here, something down here. That's what I'll do. Okay, so for our direction, like this is 1, 1, for example, let's make a random direction. So if you would like a random number that has decimal places, in the random library, here's how you do it. Python random. It's not randint, that was giving you a random integer. It's random uniform. And that gives you a float between those two numbers. So that's exactly what we'd like here. A floating point number so that it can have decimal places. Random.uniform between -1 and +1 for each of those. And so now you see, like, depending on the randomness, maybe the direction will be x offset of like -0.75 and the y offset will be like +0.25 or something. You see, like, that's how that's going to work there. So you get something, and the x and y's are between -1 and 1. And now, like, most of this is still similar, right? We're still going to that starting location. And every frame, what do we want to do? We're already kind of doing it. It's change the x and the y coordinate by that amount that the direction is saying. So every frame we were here, use the direction to move it there. Okay? That's the next step now. So we were doing that with just the y. It was just called turtle offset. But now I have turtle x offset and turtle y offset. So I'm going to be messing with all of these, so I'll just mark them global here. X offset, y offset. And then in addition to changing turtle y every frame, I'm also changing the x now, because the direction will be affecting the x. So I'll say, yes, these are global things I'd like to change. And so, yeah, this is kind of the line that needs to be added to and also changed. It's going to be, all right, change the turtle's y coordinate by the y offset, and change the turtle's x coordinate by the x offset, in some order, doesn't matter which. X coordinate by the x offset. All right, and so this is plus the, this is turtle x, change it by the x offset, and this is turtle y, change it by the y offset. Those are our names, they're up here. Okay? Does that make enough sense so far? We've added in, we've changed the name just turtle offset because it was straight up and down to turtle y offset. And now we're also adding that x offset too. So turtle x offset equals these things. Okay, so when we pick these random directions, it'll be like, all right, go a little bit to the left in the x, go a little bit to the right in the x, depending on if it's positive or negative. And same for the y, go a little bit up, go a little bit down, depending on if it's positive or negative. And if we change that every frame, I think we're going to get what we want, more or less. Look at that. Look at us moving. We have no code to check for the bounds, but we did it. That was a random diagonal direction. Isn't that cool? And we can print out every time we run our program. Let's maybe print out what our x offset is and what our y offset is so that we can kind of understand what's going on. So it looks like, oops, not t offset. That's going to have an error. Y offset. So it looks like our initial offset, do you see what it is? It's like it's positive in the x and also positive in the y, but it's more positive in the x, so it's moving a little bit faster. Whee! And then we run into an issue because I renamed things. But that's kind of cool, so it moved a little bit up and to the right that time because of those two positive offsets. What about this one? Ooh, now I got some negative. It was negative in the x and positive in the y. It was these two together. That was kind of cool, and I still get an error. That one was positive and to the left, and we're going off. So positive in both, about the same amount, so pretty diagonal. Does that make sense, how that's working? How we're getting to go sideways with those extra offsets? Isn't that beautiful? So the next thing I want to talk about is that direction, the x offset and y offset. You see how it sometimes moves kind of slow? It's nice and slow right then. But some other times, it moves a little bit faster. See that? I don't like that. I'd like, regardless of the direction we choose, I'd like to be moving at the same rate. So that it's not dependent on the randomness too. I'd like just the direction to be dependent on the randomness. Like that was pretty fast. That was faster than the last one. I would rather it move in any direction, whichever one it chooses, at the same speed, right? And the way that you get speed has to do with the length of this arrow, all right? So let's say that you randomly choose to go in that direction, and that means like just randomly you chose an x offset of 1 and a y offset of 1. Yeah? Like that's the biggest it could have been because we're going, it's a uniform value between here and here. So a random number between there and there. So and just to drive home the fact that it's got decimal places, we can do negative 1.0 to positive 1.0. So it might randomly choose like this direction, up and to the right exactly, 45-degree angle, by choosing 1, 1. It might also, right, because this is just a random number with decimals maybe, it might also choose the same direction like this. It might choose, if I can draw a straight line, it might also choose 0.5, 0.5 for the x and y offset. Do we see how that's the same direction, but because the offsets are smaller, like the ball was over here, or the box was over here, and then it'll move over here after a frame, versus it'll move a bit farther every frame if it was bigger over there. But the direction is the same. The direction is the same, just the length of that arrow, the length of that hypotenuse thing, that's smaller. And that's causing us to be slower. And likewise, we could have also chosen the same direction by choosing like 0.25 and 0.25. I don't like that. I'd rather we normalize that offset triangle so that the hypotenuse of it, let's say, should always be 1. Let's make it always 1. Okay? Like, I would like, regardless of the way we bounce off, like, think of it as a circle. Like, if we choose this direction, it's always that speed. Length 1, radius 1. If we choose this direction, it's always that speed, radius 1. Always that speed, 1, 1, 1. That's what I'd like to have. Does that make sense, what I want? And so the way to get it is after you choose your direction with your x offset and y offset, just like make sure that the length of that hypotenuse of our direction triangle is always length 1. That's what I'd like. Okay? So let's normalize it. The secret to that is going to be normalize it so that like the length of this is always 1. And if you think about it, like this is, I don't know, it's our Pythagorean theorem. This is A, this is B, this is C. What we'd like, we want C equal 1. Want C to equal 1. And to get there, we can do some math. If you think about it, like this is the length of C right now. C is equal to, like C squared is equal to the square root of A squared plus B squared. And then C squared equals A squared plus B squared. And then if you take the square root, that's just C. And so C is whatever this is. If I want C to be 1, I can divide A and B by this amount. And that'll force C to be 1. If you think about it long enough, that's what will happen. That's what we're going to do. Okay? I like to normalize the triangle that is the offset so that it's always going to be, like, regardless of how it picks that up and right direction, perfectly 45 degrees, I want it always to be length 1, right, on the diagonal. So that means we'll always move at the same rate regardless of our direction. That's what we'd like. Okay? So let's do that. Let's normalize. That's the fancy word. Normalize our direction so that it has a length 1 hypotenuse. Okay? That's what I'd like to have. So, all right, this is the math we're going to do. We have to do the square root of A squared plus B squared. And what is A and what is B? It's our x offset and y offset. So do I have math imported already? I do not. Import math so I can do the square root. And so I'll say, all right, direction, hypotenuse length currently, it currently is the square root of, no, it's not square root of A squared plus B squared, so that's the x offset and the y offset squared. Turtle x offset squared star 2 plus turtle y offset star 2. Okay, that's what I like. And so now that once I have this, if I just divide the existing x and y's by this, it will force the length of the hypotenuse to be 1. Okay, we're dividing by the original hypotenuse. If it's too small, it'll make those things bigger. If it's too big, it'll make those things smaller. Okay, so turtle x offset, whatever you were, I'm going to divide you by this length. And so like if it was too small, it'll make it bigger now. If it's too big, it will make it smaller. And it will ensure, once I do this, and I change the y offset by that same amount, same length, now I've forced. Now the length of the hypotenuse is guaranteed to be 1 after I do that. Unless one of those was 0, I guess technically you could get randomly 0, but that will eventually crash the program. But hopefully that just never really happens. It's very unlikely to hit exactly 0. But yeah, that's the idea. So now, regardless of our direction, like regardless of how we get this particular direction, we're ensuring that we always have a length 1, whatever it is, length 1 diagonal there. Okay? So now if I rerun this program after doing that normalization process, just by doing that diagonal stuff, you'll notice that regardless of which direction we pick, it's always going to move that exact speed. Just remember that speed that you just saw there. If I rerun it with a new random direction, it's always going that speed. New random direction. So it's never going to be like just chugging along. It's always going to be going 1 unit per frame in its random direction, because that's what we forced it to be. That length is always 1. Okay? That's a little weird and nitty-gritty and like technical. Does that make sense to us? Like that's a useful thing to have. Now it's just the direction that we're getting. The speed is being changed as well randomly. It's only the direction. Okay? So if we are happy, let's talk about bouncing. Because right now, like I run into an issue if we touch the top wall because I've changed the names of things. It's mostly the same, but let's figure out how to bounce now. So we have our bounding square. And just shout out if you have any questions about this stuff. I know it's technical, but it produces such a fun animation, I think. So here's our bounding square centered at 0, 0. Whee! Centered at 0, 0 there. And so this will be negative 200, positive 200. And this will be positive 200, negative 200 here. And so, let's see, this is the x equals negative 200 line. And like this is the, up here, this is the y equals positive 200 line. You can kind of see that, I hope. We would like to know when is that turtle going to hit the left wall, for example. The turtle is just grazing that left wall when what is true about it. So this is when we have to get very technical. Because of the way we stretch the turtle, the width of and height, because it's the square of the turtle right now, is 40. So the turtle is 40 by 40, and the coordinates of the turtle are always relative to its center. And so if the turtle is just grazing and exactly touching that left wall, what do we check for? It's the x value, right? Could be down here or up here. The y value doesn't matter, but we're hitting the left wall when the x value is equal to not exactly 200, but negative 200, but exactly negative 180. See that? It's half of his width. Half of that width there. So the turtle has hit the left wall or has tried to exceed the bounds of the left wall when the x-coordinate of the turtle is less than or equal to negative 180. Do we see that? That's one thing that we'll check for. Okay, so it's not negative 200 really, like I lied about last time, but it's negative 180. And likewise, when it's over here, that means the turtle is just grazing the wall when the x value is equal to positive 180. If it's any bigger than that, we've also tried to go outside, and that's possible too. So make sure to rein the turtle back in. But we've hit the right wall, or we've tried to exceed it if the x-coordinate is bigger than positive 180. And then for the top and bottom wall, it depends on the y, right? For the left and right, it didn't depend on the y, only the x, because the turtle could have been in any of these places and still grazing it. For top and bottom, it's all about the y. Yeah, and so that's what we've already done for the bouncing program from before. The turtle is hit and just graze this wall when the y is equal to positive 180, or you're trying to try to go bigger than that. And then we also hit the bottom part of the wall when the y is equal to or less than negative 180. Okay, I hope we see that. So yeah, that's how we know when we've hit a wall. And the question is, how do we bounce off properly? We learned this last time. It's going to be negating, like if it's a sidewall, it's the x offset that we would negate of the direction. And if it's the top or bottom walls, it's the y offset that we're going to negate as part of the direction. And that will produce the proper kind of bouncing. Okay? So let me show that to you. So here's this. Here's what I mean by that. Let's remember it from last time. Then we'll package this idea into a function too, once we get it working at least. So let's say here is my turtle, not drawn to scale, and like he's just grazed that left wall, and he was trying to go this way, right? So we came in this way, we hit the wall, we must bounce off, or we came in, hit the wall, bam, we hit the wall, we want to bounce off that way, right? We came in at a sharper angle like that, we want to bounce off at like a sharper angle. Okay, so that's what we would like to do. And so we were coming in this way. This was our direction, for example. It was go this amount in your x offset, so a little negative for the x and a little positive for the y. All right, y offset. We were coming in this way, we want to bounce off that way. So we were like, bam, bam is what we would like to do. And so the new direction we'd like to have, you see that it looks the same. It looks about the same. The length is the same, right? It'll always be length 1. And we're still going up by the same amount. You see how this bit right here, the y offset, that's equal. It's still going up, positive y offset, as it was. But instead of this x offset going to the left a little bit, we're now going to bounce off and go to the right a little bit. See how that produces the proper kind of bouncing, kind we'd like to have. So whatever our new x offset is, it's just the negative of what we had before. Does that make sense? And so same thing's going to happen for this wall. When we're coming in this way, right, if we came in that way and hit that wall, that means we were going a little bit to the right and a little bit up. We would like to bounce off exactly kind of that way, yeah? Which means still go up a little bit, but go left now. Go left and up. See that? That's what we like. Go left, then up. And so it's just that x direction switches. So we're going to negate our x offset. That's the secret, okay? And same for the top and bottom. It's just the y offset instead. So if we hit the bottom wall, maybe we came in like this was the direction that brought us here, then that means, how do we get there? Our x offset was positive and our y offset was negative. We're going down and to the right. We'd like to bounce off up and to the left. Or sorry, down and to the right. Yeah, we'd like to bounce off up and to the right, sorry. Up and to the right still. Which means same x offset, still go right, but we were going down, we now want to go up. So you see how that means negate, take your same x offset and negate the y offset. It was like negative, make it now positive. So that's all the technical details that will give us bouncing. Okay? And so we've already got this mostly. We've got it here. If we hit, this one is going to be, let's see, we'll just get rid of this comment, I think. So instead of saying negative 180 and hard coding it, but because you could change the size of the turtle if you'd like, we're just going to do turtle width over 2, and that will be 20. So this really is negative 180. That's perfect. So this is the bottom wall, where we tried to exceed it. This is the top wall, where we tried to exceed it. Let's do the same for the left and the right wall. All right, so this was, if we hit the top wall or the bottom wall, we'd like to negate our y part of our offset. So it was turtle y offset becomes negated. Change the turtle y offset. So we need to move upwards now. Change the turtle y offset so that we move downwards now if we hit the top wall. So that's what needs to change there. That's the y offset that needs to change when we hit the top and bottom. And then the left and right walls, it's the x offset that needs to be negated. So it's really these ideas all over again. I'll just copy and paste them, one for each. And it has to do with the x. So if turtle x is less than or equal to this, that means we hit the left wall, or we're trying to go past it. Move the turtle back inside, just make sure the x is that. And then change the turtle x offset so that we move, I guess we were coming in, if we hit the left wall, that means we're coming to the left a little bit. We need to move rightward now, to the right now. Okay, that's the idea. So turtle x offset becomes negated. That's exactly this idea. We're coming in with a negative x offset, negate it so that now it's a positive x offset. Keep the y. Right? That's how you get your proper bouncing. And I think I'll just copy this one again, and we'll do that for the right wall. Okay, so for the right wall, that means our x-coordinate is greater than or equal to 180. So that's equal to, if our x is equal to or trying to exceed this guy, that means we either hit the right wall, or we're trying to go past it, move the turtle back inside, make him exactly positive 180, and then change the turtle x offset to hit the right wall. That means we were coming in the rightwards direction. Now we need to negate the x part of our offset so that we go out into the leftwards direction, to the left now. Does that make sense? So now it's 4 if statements. And actually, they actually do have to be if statements, because think about it. Let's see. We can't use elifs. You could use them for the x and the y. You could use them for the top and bottom. This one right here could have been an elif. It could have been connected to this original if statement. And this one also could have been an elif. Could be connected to the left and right, because you can't hit both the left and the right wall. You see that? These are never going to happen at the same time. So this could be if elif. It's like one or the other. But I'll just keep them separate. But this whole thing could not be one long if elif else kind of thing. Okay? You couldn't do that because it's possible you hit the corner like you did in the Office episode. Because if you come out and you hit the corner, that means you both hit, like this was hitting the top wall and the right wall at the same time. And so you need both of these if statements to fire. You need this one as well as this one to fire. See that? You need both of them to do their action so that you move down and to the left now. Does that make sense? So to produce that opposite direction, just in case you hit a corner on the same frame, these should all be separate. Okay, that's the idea. At least the left and right from the top and bottom, because it's possible that you do hit the top or the bottom and the left, or the top and the right at the same time. And so we don't want to have just one if statement fire. In that case, we'd like both of them to take over, whichever two apply for that particular corner that you hit. Okay, that's a little weird, but that's the idea there. Okay, so if we are happy, I think that was the bulk of the work. So it's a little ugly right now. We'll clean this up in a little bit, but what we do every frame, right, is move by our current direction. And if we hit a wall, we know how to check for that. Now we've checked for top and bottom, and now we know how to check for left and right. And what do? We manipulate one of the pieces of our offsets to bounce off in the right way. Okay? And that, I believe, if I didn't make any typos, is going to give us bouncing. Wow. Isn't that cool? Ooh, is that going to hit the corner? No. Darn. We'll have to wait. But that's the reason. That's the reason we have multiple if statements, because you could be hitting both the top wall and the left wall at once, and we want to have both of those pieces to reset the offsets happening at the same time. And then down here, of course, once we've figured out where to put the turtle, actually move them there with the go-to. Ooh, that was almost the corner. That was beautiful. I love it. So yeah, every time it's different. It's a random initial direction, and so you get a new fun animation every time. But that was the secret. This is mostly up and down. You see how it's moving to the right just a tiny, tiny bit. That's the magic of random directions, but it's always moving at the same speed because of the way we normalize things. It just ever so slowly bounced off there. But this is so satisfying, I think. Are there any questions about how this is working? Yeah.
If you scroll up to the code.
Sure. That's this bit right here. So here we are calculating that length of that hypotenuse, just in case it was like less than 1 or bigger than 1. And then we're dividing each individual offset by the length of that original hypotenuse. That will offset them. And like if it was smaller than 1, you're dividing by a number that's smaller than 1 to make them bigger. And if it was bigger than 1, you're dividing by a number bigger than 1 to make them smaller. And so that'll force that hypotenuse length after that's finished to be length 1. Does that make sense? Yeah, so that's that code there. And again, it's different every time. It's so, so cool. Any other questions about this? So I'll be giving you this code. Please play around with it. It's so satisfying to just watch it work, and like you can change the speed of things, right, by changing the length of the hypotenuse. I'll do that in just a second. Let's clean this up a little bit first. Well, let's take this code that we have, and I think DrawFrame is doing so much right now. I can't even show you all of DrawFrame on one screen. So I think a better way to do this would be, let's make a bounce if we hit the wall function, just like we had in Scratch. And I think that would make it better. So like in DrawFrame, repeatedly, or not, yeah, inside of DrawFrame, what I'd like to do is like take all these things, take all these pieces, these if statements, and just like package them all together. So like DrawFrame is easy. It's just like, all right, change the turtle's x and y coordinate by a certain amount, and then just like if we hit a wall, bounce off by just calling our function bounce if hit wall. See how easy it is to like understand DrawFrame if we did it that way? And then we could take the rest of that, the rest of those ideas of bouncing if hitting walls, and put that into a function. Def bounce if hit wall, and we'll put all those if statements there. And these if statements, though, they are messing with turtle x, turtle y offset, turtle x offset, and so those are global variables. We have to mark them just like we did here. So we're allowed to change them. Okay, so I think that's a bit cleaner. So this is just like, this is how we bounce if we hit the wall. Like we're checking for the bottom, top, left, and right with our 4 if statements. They're all separate things. These could be tied together with an elif. These could be tied together with an elif, though. But the rest of them need to be separate. And now DrawFrame is easier to understand, I think. It's just like, all right, every frame, repeatedly, I draw a frame. What does it mean? Well, I move a little bit by my current direction. Just in case that took me off the edge or hit the wall, I'll bounce off. And then, all right, now I've changed. Like maybe this changed where the turtle is now. It's definitely maybe changed the offset, too. Then we'll redraw that turtle. Okay? So that's a bit easier to understand now for DrawFrame, and nothing has changed. Nothing has changed. We still have the same program. Whee! Ooh, that might hit the corner right there. Oh, that was so close. So nice. Okay. So, yeah, that's the idea there. So everything still works as before, but DrawFrame is a bit easier to understand, I think. That's the whole point of making functions. Just like, make it cleaner for you to come back later and understand what you were doing. Okay? And there's bouncing if hitting wall. Another question? Yeah.
Sorry, mine. The way I wrote
All right, I'll give you 30 seconds to look at it. But yeah, I'll also give you this code. So yeah, every frame, we're checking, we're changing our offset by our current direction, and we're moving that in the x and the y positions because our offset is taking us a little bit in the x, a little bit in the y in a certain way, always length 1 though, thanks to our normalization. And then we are checking like, oh, did the x get so small that we've hit the left wall? Did the y get so small that we've hit the bottom wall? Stuff like that. So that is the secret. And then we just make sure to change the correct part of our offset. Like this is about to change the y part, the x part. And that bounces off in the nice, correct, satisfying way that we know and love. So yeah, I think that's a good thing to say. And then also, notice that we've normalized the length of that hypotenuse at 1. That was our speed. We're moving 1 unit every frame right now. If we'd like to move faster every frame, we can change the length of our hypotenuse very easily. Right now, it's guaranteed to be 1. If I'd like it to be like 2, x offset, I might have to multiply by the square root of 2, actually. I don't remember. But I'm either, like you can multiply it by 2 or something. Turtle x offset times 2. We can speed it up by twice the amount, essentially. I think this might speed up by a little bit more than 2, but you get the idea. You might have to do some extra math to determine the new length of the hypotenuse, but you can make it like maybe a little bit over twice as fast, right? By multiplying the x offset and the y offset, because they're set now. The length is a normalized thing. You can change them a little bit more now, or you can just like hook into this and be like, all right, take all this. The order of operations works out. Now it's like times 2 times 2. Now the length of the hypotenuse is like 2 or so. It might be different. I don't have the math deep down in my head right now, but that's kind of the idea. All right, it might be a little bit more than 2. But if you do that kind of multiplication, that changes the length of that hypotenuse. Okay, so this is maybe a cleaner way to do it. But do you see now that, all right, we're going to move more than 1 every frame now. It's like at least 2, maybe more. Whee! So now it's speeding. It's going very fast. 2 units per frame-ish. You could do 3. You could do 5. Like, it could be going off really fast. But that's like the length of that triangle. That our direction triangle. Now it's going way too fast. And so that's pretty fun. I don't know. It's fun to play around with. You can change the square to a circle. You know a lot of things now. I've shown you a lot of things. And so maybe let's keep it 1. But that, I think, is the program I wanted to show you today. The one I promised you. It's so fun. So it's a good one to study for sure. Any other questions before I switch gears? So it's so satisfying. Take a look at this code when I give it to you. This was fun to write for sure, but we built our way up to it. All right, so if we're happy, the next thing I'd like to do is show you how to move with the keyboard. Use keyboard stuff to change like the direction of things, to change the position of things. Because actually the goal, like if you don't know where I'm going with this yet, the goal of these slides and like the previous ones as well is like I'd like to make Pong for you. I'd like to come full circle because we made Pong very, very early on in our Scratch days. I want to make Pong for you in Python. So right now we have the ball now. We've made the ball for Pong essentially by doing this. The next thing we need to do is make the paddle. And the paddle moves with like the keyboard or the mouse. You can do mouse stuff too with the turtle module, but let's do keyboard stuff instead. I think that'll be a little bit easier. So we're going to be able to do the following. We're going to have like a little paddle, and we'll move that paddle with our key presses. Like our up arrow will move it, our down arrow will move it a little bit. It's like we're gonna have something that looks like this. I'll move it up and down. Okay, that's the goal. So we can do what we were doing like this. This is like our Pong game. We can still draw the bounding square. We can still use the turtle as the paddle now instead of the square. We'll just stretch them a little more in the Y direction than the X direction. So we can take a lot of what we've been doing, but we also need to hook into the keyboard, and I'll show that to you. Okay, so let me steal this program, 2D Bounce program, and then I'll make a program just for the paddle for Pong, paddle.py. All right, so let's get started and do. I don't need draw frame. I don't need any of this bounce of hit wall stuff. I do need like a starting location. That'll be there. I don't need like directions. I don't need X offsets and Y offsets. So I'll be hard coding all these things away in just a second. But we'll make it work. Okay. But I still want to draw the rectangle, and I still want like the turtle to be somewhere. So this will get us most of the way there. But I'd like the turtle to be the paddle. All right. So this was the turtle stretched evenly in each direction. To make the turtle the paddle, it needs to be stretched a whole lot more in the Y direction. And here's a good amount of stretching that I discovered last time. If you stretch the turtle by 1.5 in the X direction and 6 in the Y direction, that's like a good paddle looking thing. Okay? So if we do 1.5 here and 6 here, they'll be happy. Okay? So that'll work. That looks like a paddle to me, so that's pretty good. So then we need to just place the paddle in a nice spot. So let's change some variables to start at least. So this was our, this is our bounding square. We got that already. Make the turtle not the square this time. Make the turtle the paddle. So the turtle will be a square shape, but because of that stretching is going to be a paddle now. And so maybe we should be saying not like turtle width, but like paddle width. I guess we don't even need to keep track of the width right now because the width is different from the height. It's like 30 and 120 or something. So instead of like turtle X, let's maybe call it paddle X. Instead of turtle Y, we'll call it paddle Y. And we'll have to give like a starting point as well. We'll figure out if that's a good one. And then like turtle go to paddle X, paddle Y. That's the goal. Okay. So I think pulling happens with the paddle on the left side. So I think we'll have to change. We'll have to maybe hard code the x value to be pretty small, close to over here, and the y value, maybe we can make it just start in the middle always. That could work. So if like the y of the paddle is always 0, that could work. And then I guess this comment makes no sense anymore. It's like paddle x is some negative number, like negative 170, I think worked well before. And then if we put the paddle y, hard code that to 0, that'll force it to be in the middle of that square. So negative x to be over the left, and then 0y to be straight in the middle there. So that's a good spot for the paddle. Okay, so that seems right. And the rest is, let's hook it up to the keyboard so that when I press buttons, like the paddle moves. So here's the secret. There is something called on key press for the turtle. The turtle, if you use that, will be listening to our key presses. On key press. There it is. And so they're doing it in a weird way, but the secret is, like, you say turtle.onKeyPress, you say the name of a function you'd like to call every time a certain key gets pressed. You give the key as a string, like the up key, the down key. It'll call a function for you. If you just supply its name, it'll call that function every time that key gets pressed. So we can make like a move the paddle up function and move the paddle down function, and then the turtle will call those for us when it sees us pressing those keys that we care about. Okay? So that's the secret. We're going to say turtle.onKeyPress, give the name of a function like move up, and then supply the up arrow as a string. So this is kind of cool. Even if you programmed C++ before, you probably haven't done this before, you can pass functions to other functions, because that's kind of what's happening. OnKeyPress is a function. You're passing a function to it, and it'll just call it for you later. Just kind of powerful. It's really cool. Yeah, there's that. And then there's also, it goes hand in hand with something called turtle.listen. What you do is you set up the on-key presses, maybe for the up arrow, for the down arrow, for the space bar if you need that too or something. And then once you're done setting up the key press handlers, that's the technical term, then you say turtle.listen to be like, I'm ready for you to start listening for my key presses now. I've got everything set up. So that's like the last piece of the puzzle there, the turtle.listen. Okay, so let's make that happen. Let's make a function to move the paddle up and a function to move the paddle down, because this is what I'd like to have happen. I like to say this. Set up functions to run every time the up/down keys are pressed. Okay, so I'll say turtle.onKeyPress. Maybe I'll make a function called go up. That'll be the function's name. And then I want it to be called every time I press the up arrow key on the keyboard, and you indicate that by passing along a string with the name of the key. So just capital up. And I'll make a same for the go down. We'll make a go down function that we want to get called every time the down key is pressed. And then once that's set up, then I'm ready to say turtle.listen. Do those things every time those keys get pressed. All right? So that's the secret. Now I just need to make a go up function and a go down function, and the turtle will call those for me whenever it notices me pressing them. So def go up, and I'll do the same for go down. Def go down. Okay, and so what should go up do? Make it go up. What does that mean in terms of our variables, though? What should we be changing? I have a paddle X and a paddle Y. What needs to change if I press the up arrow? What part? How do we move it to here? What does it mean to move it to there? What was that? Very good. Yeah, so we want to go up in the Y direction. Add to the Y. Very good. So how much do we want to add every time? That's up to us. You can play around with that. But I'd like to say something like paddle Y equals whatever it was, plus 10 units or so. That'll work. And because this is a function and it's modifying a variable that was defined outside a global variable, I have to mark it as global. Global paddle Y there. Okay? That's the secret. And so I'm going to modify that, make it there. And that's kind of what I want to have happen for that one. And same for go down, right? I'm going to modify the Y. It's just go down in the negative Y direction. So subtract from your existing Y, make it smaller. See that? So if I call these two functions every time, the turtle will do it for me, every time I press those arrows, then this is what I get. So I'm pressing the up arrow. Nothing's happening. Pressing the down arrow. What? Nothing's happening. Something's wrong. Well, does anybody see it? I'm pressing these. It is calling the functions. Well, it's not happening. It's not moving the turtle. Paddle X and paddle Y, they're just variables. They have nothing to do with what's on the screen, do they? How do I make it apply now to the screen? I say turtle.goto. That actually moves the turtle to those places that I've recalculated them to be. See that? That's what I was missing. So now when I press it, it does change the variables, and then also it's going to actually move the turtle to those new places. And you can hold it in. I'm just like choppy though, but it works. And one thing that's not correct right now is I can do that. Yeah, I can go way up there or way down here. I don't want that. So I want to like make sure to cut it off if I try to go too far. And so we're going to need some if statements. We need to check. We need to make sure we're not going outside the bounds here. So, okay, how do we do that? What does it mean to be the paddle just grazing the upper part of the window? It's always relative to the center of the paddle. Like it's the y that we're changing. This is like y equals positive 200. We don't want the paddle's y to get any bigger than this, right? See, that's the center point when you're hitting that. What is that? Something like that, yeah, 3, because we stretched it by 6. It was really weird the way we stretched it, and so the secret is because we stretched it by 2 last time, and that made it 40 by 40, so that means the original size was 20. The original size was 20 for the ball, or for the square. We stretched it by 1.5 in the x direction, which made it 30 on the x, 30 width, and 6, stretching by 6 makes you 120. See that on the height there? So that means half of your height for this paddle is 60. And so this is y equals 140 that we don't want to go past. Does that make sense? That's the silly math that we got to do now. But that's the secret. Okay? And so that's what we'd like to be. We don't want the y to ever get bigger than positive 140. And I think you can imagine we want the same to be true about negative 140. Right? Don't go past that either in the negative direction. So this is the one we just talked about, though. Let's, all right, make sure we don't go past the top. Okay? So if, what do we just calculate? If the paddle's y is 140 or any bigger than that, paddle y is equal to 140 or any bigger than that, so greater than or equal to 140, I would like to make sure the paddle only grazes the top, like bring it back down. If I ever tried to exceed it, bring it back down to 140. And then, like, don't ever let it go past it. And this if statement will just make sure that's true. Like, if it ever tries to go past it, it'll just bring it right back. And so it will never get bigger than 140. And so that means we'll never move the y, really, with the go-to, past 140. See that? That's exactly right. It'll be negative 140 there. So here I am pressing the up arrow. I'm still pressing it. I'm holding it in, but it's being restrained, which is nice. Okay, so let's do the same one for the bottom there. Make sure we don't go past the bottom. And so, like, we try to go there. That's what this first line does. Try to move it down, but don't go too far. If we try to go past the bottom there, that means it's less than or equal to negative 140. It's just like, it's symmetric, right? If it ever tried to go past the bottom, then just like rein it back in. If it was equal to, technically I didn't really need this. If it was equal to, just keep it there. But less than or equal to makes sense to me. If it ever tries to go past the bottom, make sure that's as low as it can go. Like paddle Y will take over here and make sure when we actually move the turtle, we're never going too far down. So those two working together, those two functions are getting called when I press those buttons. Up arrow, I'm being held back, perfect. And then same for down, holding in the down button, but I can't go any further, which is exactly what I'd like to have happen. Any questions about that? Does that make enough sense? Very similar stuff, but we've got both pieces to Pong now. That's really exciting. All right, so of course the trick is hooking them together properly, and maybe before next programming lecture you can try that yourself. See if you can get them hooked together. See if you can figure out what it takes. So yeah, that is I think everything I want to talk about today for 2D bouncing. Yeah, if we're good, let's see, make sure to do that attendance. I see that I kept it going. But we talked about the final already, and that was really the last thing. No new assignments this week, so as long as you understand what's going to happen for the final and you have no questions about it, that was all that I wanted to talk about today.